All right, so in this video we're going to talk about interpreting correlations and the effect of outliers. So we have to look at outliers and their effects carefully before interpreting a correlation. We should not remove outliers unless we have a strong reason to believe that they do not belong in the data set. So if you recall that an outlier is a data value that is extreme compared to most other values in the data set. So here is a blow up of this graph. So we have a bunch here and we have one out there. This makes it appear like there is a positive correlation going on, but that almost looks like it's an outlier. So you'd have to have a good reason to take it out and then say like there's no correlation instead of being a positive correlation, okay? So the correlation may be coincidence. Both correlation variables might be directly influenced by some common underlying cause, or one of the correlated variables may actually be the direct cause of the other. So even in that case, it may be just one of several causes. And that's referring to that the correlation does not imply causality. In general, correlations can appear for any of the following three reasons. I forgot to read the title, so sorry. So correlation does not imply causality, like what caused it. So there's three reasons that you can have correlation. They can be a coincidence. The correlated variables might be directly influenced by an underlying cause that's common to them, or one actually may be the direct cause of the other. All right, so the example one, we're going to talk about mass correlation. You've conducted a study to determine how the numbers of calories a person consumes in a day correlates with time spent vigorous bicycling. Your sample consisted of 10 women cyclists, all of approximately the same height and weight. Over a period of 2 weeks, you asked each woman to record the amount of time she spent cycling each day and what she ate on those days. You used the eating records to calculate the calories consumed each day. So the scatter plot here shows each woman's mean time spent cycling on the horizontal axis and the mean caloric intake on the vertical axis. Do higher cycling times correspond to higher intake of calories? So if we look at a blow up of our graph here, so these are our times here, or our data points. We've got a couple that are sitting out here, and then we've got this one. So if we look at the data as a whole, your eye will probably tell you there's a weak positive correlation in which the greater cycling times tends to go with the higher caloric intake. In fact, the correlation coefficient in this is only 0.374, so that's kind of low. However, if we look at these two outliers that are far away from there, one is representing a cyclist who cycled about a half hour per day but consumed more than 3,000 calories, and the other one cycled for 2 hours a day on only 1,200 calories. So, and that would be that one down there. So it's difficult to explain the two outliers given that all the women in the sample have similar heights and weights. We might suspect that those two women either recorded their data incorrectly or they were not following their usual habits during the 2-week study. If we can confirm the suspicions, then we could have a reason to delete the two data points as invalid, that they weren't really doing what they were supposed to do in the study. We can say, hey, we can delete those. Now, if I delete those two outliers, this is what my graph looks like. Now this looks like we have a strong correlation without the two outliers. And it suggests that the calories consumed rises by a little more than 500 calories for each hour of cycling. Now, again, we can't just remove the outliers unless we can confirm what we think happened. Otherwise, you can't just leave them out. But it changes the outlook. If we take those away, it looks like we have a more positive correlation. Okay? All right. So the answer to that would be, it's kind of a mixed thing that if we don't look at those outliers, we can definitely see that the higher they're cycling, the more intake of calories they do because they're burning all that energy, so their body's looking for fuel. All right, so the explanation of correlations. Decide which of the three possible explanations is most likely for each of the following correlations. The correlation between infant mortality and life expectancy. So, infant mortality and life expectancy. Well, typically what's going to happen with that, so we are in 7.2, is between infant mortality and life expectancy, there's a common underlying cause, and they're all going to respond to the quality of health care. Quality of health care. Okay, if the quality of health care is good, then you're typically going to see less infant mortality, and if the quality of health care is good, you're going to see a longer life expectancy. So it's a common underlying cause. And that was the second point that we talked about when we were looking at the causality. So B, we have the first 5 subjects are all males, and the last 5, wrong one, sorry. The correlation between the amount a person smokes and the likelihood of lung cancer. All right, so what's the correlation of that? Well, we've talked about this a couple of times. Smoking causes lung cancer. So there is a correlation that happens there. So the correlation, this would be a direct cause, right? Is smoking causes lung cancer. It's been proven many a times. All right, and then part C, let's go to the right question here. The correlation, negative correlation between the price of a product and the demand for the product. Well, usually it's going to be causal, right? There's going to be a causal correlation with that. Higher prices lead to lower demand, right? So between the price of a product and the demand for a product, we're looking for a negative, not a positive, but a negative. So if I rise the price up, the demand will go down. So it's like right now we have high gas prices, right? So if the gas price is going up, people are trying to drive less, so maybe the demand goes down a little bit. Or even on some of the groceries. Groceries are up. You still got to buy groceries, but maybe you're buying less frivolous groceries, like snacks and that. Could be. So, and it also, like early on, the electronic things that would come out, they were high, so not everybody bought them. But as the prices went down, everybody then owned a DVD player or a VHS player. You used to actually rent the VHS players because they weren't in the store to buy. It's like you went and rented the movie and you rented the machine as well. All right, so this is causal. Causal. Higher prices lead to lower demand. But usually if the prices are low, then people will do more with it. All right, example 3. The table lists footprint length and height, they're both in centimeters, of 10 subjects, including both men and women. Use either a scatter plot or a formula for the linear correlation coefficient to determine whether there is a correlation between the two variables. So what I could do here is I could plug all these points, again, back into my calculator using my stat method. I'm not going to do that on this one because you've seen me do this a couple of times on the previous video. Right? Yes. And if you're just looking, look for the video for seeking correlation. I go through a whole demonstration on plugging those into our calculator. And in fact, in that video, I talk about all the steps that you need to do that. So you would go back and do all those steps to find the R factor. So we can go back through and look at all of that, and it would create us a scatter plot, and it will give us the R factor. So you could use either one. All right, so for that one, so this is example 3. If I'm looking at that, the R factor, this will be part A, will become 0.853. And if it's at 0.853, then that means there's going to be a positive correlation. We could even say it's a positive strong correlation because it is at 0.8. So I would consider that to be a strong one. All right, for part B, the first 5 subjects are all males, and the last 5 subjects are all females. For the males, again, use either a scatter plot or a formula. So we're going to go back and do the same thing we would have done here using our calculator, or you can do it on Desmos. Remember I told you, you can go to desmos.com and put these in as well if you don't have a TI-8384. And you go over to the top left 3-line thing, click on it, and go down to I think it says statistical regression. Yes, statistics linear regression to desmos.com, and it'll let you plug all the numbers in and see it. So for part B, our correlation coefficient will be R equals 0.932. Again, this will be a positive correlation. This is for the males. So the males are all positively correlating. And then for part C, it says the first five subjects are male and the last 5 are female. For the females, use the same type of thing and determine if there's a correlation between the two variables. So 1, 2, 3, 4, 5. So the first 5 were the male. So they're seeing that there's a correlation. As this gets bigger, that got bigger. Okay, so a positive correlation. And on this one, this is their height for women. And then here is our shoe size. Okay, or not our footprint length. The footprint to the height in centimeters. All right, so what we discover on part C is that the R factor is a negative 0.302. So this is actually a weak negative correlation. And on these, we could say this is strong on each of these. This one is actually weak. This one's weak because we've got a negative 0.3. So the negative number tells us it's negative. 0.3 says there's not as much correlation going on with the women or the female versus the male. And D asks us, does the results make sense? Do they make sense? So, it doesn't make sense to me that there would be a positive, strong correlation for men and a weak negative for females. So, what we could look at is that the sample size is small because we only have 10, right? Does not make sense because there's a strong positive for the males and a weak negative for the females. You would think it would be if the men were strong, the women would be strong, or if the men were weak, the women would, for the correlation goes. So we're probably thinking it's a relatively small sample size because there's only 10. All right. And then number 4 doesn't make sense. If a scatter plot shows no correlation, then there cannot be any relationship between the two variables. Absolutely no correlation. Well, it doesn't make sense. Let me give you some reasons why. Does not make sense. So there may be a relationship that's being masked by outliers. We've talked about that in the beginning. So if we have that graph, remember, here we had those happening. And so the outliers can cause that. So it could make an inappropriate grouping of our data. It's also possible that the sample didn't show the relationship that exists in the population because of the sample. So we could see masked outliers. And then the other is that the sample does not show the relationship in the population as a whole, right? In the population. So usually our samples are showing us what we're expecting to see in the population, but in this case it may not show that relationship in the population because of something going on. All right, so make sure you're doing your homework. This is just interpreting correlations. In the next video of best fit lines and prediction, we'll be doing some more on our calculator using our buttons in there so that we can see what's happening in with the best fit lines. All right, because that's what's coming up next is best fit lines. So again, if you're watching this and you're like, hey, I wanted to see that, you can watch the best fit lines and prediction, and you'll see me do the calculator. Do your homework.